Introduction to Rogue Planets. Definition and significance. In the vast expanse of the universe, where stars and galaxies populate the cosmic landscape, a peculiar category of celestial objects has captured the attention of astronomers: rogue planets. Unlike planets that orbit a star, rogue planets wander through space unbound by a solar system. Their existence raises intriguing questions about planetary formation, the dynamics of stellar systems, and the potential for life in the cosmos. Definition of rogue planets. Rogue planets, also referred to as free-floating planets, are defined as planetary bodies that do not orbit a star. Instead, they traverse the galaxy independently, often resulting from complex gravitational interactions or processes that lead to their ejection from their original systems. These planets can vary significantly in size, composition, and temperature, ranging from gas giants like Jupiter to smaller, rocky bodies akin to Earth. The term rogue implies a certain sense of rebelliousness, highlighting the contrast between these solitary wanderers and the more familiar planets that reside within stable orbits around their stars. Estimates suggest that there could be billions of rogue planets within our Milky Way galaxy alone, potentially outnumbering the stars themselves. This raises fascinating possibilities regarding their formation, evolution, and the role they play in the broader cosmic narrative. Overview of their discovery. The discovery of rogue planets has been a relatively recent development in the field of astronomy, largely facilitated by advancements in observational techniques and technology. The first strong evidence of a rogue planet was presented in 2006, when astronomers detected a planetary mass object, later named PSO J318.522. wandering through space approximately 80 light-years from Earth. Utilizing a combination of infrared observations and gravitational lensing techniques, researchers have been able to identify several more rogue planets since then. As observational technology continues to improve, particularly with the advent of space telescopes and more sensitive instruments, the hunt for rogue planets has gained momentum. The upcoming James Webb Space Telescope, JWST, and other next-generation observatories are expected to significantly enhance our ability to detect these elusive celestial bodies, offering insights into their properties and distributions. Significance in astronomy. The study of rogue planets holds profound implications for our understanding of planetary formation and evolution. Traditionally, it was believed that planets formed in a protoplanetary disk around a star, gradually coalescing from gas and dust. However, the existence of rogue planets challenges this paradigm by suggesting alternative pathways for planet formation. For instance, they may form in isolation or result from dynamic interactions within a star system that lead to ejection. Furthermore, rogue planets can contribute to our understanding of the dynamics of stellar systems. Their presence may influence the orbits of other celestial bodies and affect the gravitational landscape of their surroundings. This can lead to a reevaluation of how we understand planetary migration and the stability of planetary systems. In addition, rogue planets may harbor unique environments that could potentially support life. While their lack of a star means they do not reside in traditional habitable zones, some rogue planets may possess internal heat sources or atmospheres that allow for the existence of liquid water. This possibility expands the search for extraterrestrial life beyond the conventional bounds of star systems. Moreover, rogue planets can provide valuable insights into the history of our galaxy. By studying their distribution and characteristics, astronomers can glean information about the processes that have shaped the Milky Way over billions of years. These insights can help reconstruct the evolutionary history of planetary systems and the broader galactic environment. In summary, rogue planets represent a fascinating and enigmatic class of celestial objects that challenge our conventional understanding of planetary formation and dynamics. Their discovery has opened new avenues of research in astronomy, prompting scientists to reconsider the processes that govern the formation and evolution of planets. As we continue to explore the cosmos, rogue planets will undoubtedly play a key role in unraveling the mysteries of our universe, offering glimpses into the diverse and complex nature of planetary systems that exist beyond our own. Section 1. What are rogue planets? Rogue planets have emerged as a captivating subject of study within the field of astronomy, representing a unique category of celestial bodies that defy traditional classifications. In this section, we will explore the characteristics and classification of rogue planets, as well as the fundamental differences that set them apart from traditional planets. Characteristics of rogue planets. Rogue planets are defined primarily by their lack of a stable orbital relationship with a star. Instead of being tethered to a solar system, these planets wander through the galaxy as solitary entities. This independence gives rogue planets several distinctive characteristics. 1. Variety in size and composition. Rogue planets exhibit a wide range of sizes and compositions. They can be gas giants comparable to Jupiter, small rocky bodies similar to Earth, or even icy worlds reminiscent of Neptune. Current estimates suggest that rogue planets may vary from a few times the mass of Earth to several times that of Jupiter. This diversity challenges our understanding of planetary formation, as different processes may lead to the creation of these varying types of planets. 2. Temperature and atmosphere. Because rogue planets do not receive energy from a sun, their temperatures can vary significantly. Some may be extremely cold, drifting through space at temperatures close to absolute zero, while others could be warmed by internal heat sources, such as radioactive decay or residual heat from their formation. The presence of an atmosphere on rogue planets remains a topic of debate. Some may have thick atmospheres capable of supporting complex chemical processes, while others may be barren and devoid of significant atmospheric activity. 3. Formation. The origins of rogue planets are still being investigated, leading to several theories regarding their formation. One prevalent idea is that they are formed in a similar manner to traditional planets, coalescing from gas and dust in a protoplanetary disk. However, instead of settling into a stable orbit around a star, gravitational interactions can lead to their ejection from their original systems. Another theory proposes that rogue planets could form through direct collapse of gas clouds, resulting in a planetary body that never becomes associated with a star. Classification of rogue planets. Rogue planets can be classified based on various criteria, including their mass, composition, and formation processes. Here are some common classifications. 1. Mass classification. Sub-brown dwarfs. These are the smallest rogue planets, typically with masses below that of typical stars, less than about 13 Jupiter masses. They may not be capable of sustaining nuclear fusion like stars, but can still exhibit some planetary characteristics. Super-Earths. These rogue planets have masses exceeding that of Earth, but are less massive than Neptune. They are of particular interest because they may have the potential to support atmospheres and possibly life. Gas giants. These are large rogue planets that possess significant gaseous envelopes. Their size can be comparable to or greater than that of Jupiter. 2. Composition classification. Rocky rogue planets. Similar to terrestrial planets, these bodies have solid surfaces and are composed primarily of rock and metal. They may share characteristics with Earth-like planets, Icy bodies. These rogue planets are composed largely of ices and may have surfaces covered in frozen compounds, such as water, methane, or ammonia. Gas-rich planets. These planets possess substantial gaseous atmospheres, making them similar to traditional gas giants. Differences between rogue planets and traditional planets. Understanding the distinctions between rogue planets and traditional planets is crucial for appreciating their significance in the universe. Here are some key differences. 1. Orbital dynamics. The most fundamental difference lies in their orbits. Traditional planets are gravitationally bound to stars, defining stable orbits within a solar system. In contrast, rogue planets lack this stable gravitational relationship, enabling them to drift freely through the galaxy. This independence from stars leads to a vastly different environment, where rogue planets are subject to different physical processes. 2. Energy sources. Traditional planets receive energy primarily from their host stars, which influences their climates, atmospheres, and potential for life. Rogue planets, lacking a nearby star, must rely on internal heat sources or residual warmth from their formation. This absence of solar energy fundamentally alters the conditions on rogue planets, often resulting in extreme cold and unique atmospheric dynamics. 3. Potential for life. The search for extraterrestrial life is often concentrated on planets within habitable zones, where conditions allow for liquid water and stable climates. Traditional planets within these zones are prime candidates for hosting life. Rogue planets, however, present a different scenario. While they may not reside in conventional habitable zones, some rogue planets could possess subsurface oceans or geothermal activity that might support life, albeit in a very different context. 4. Formation and evolution. Traditional planets are typically formed from the accretion of material in a protoplanetary disk around a star. The dynamics of their formation are influenced by the gravitational interactions with their host star and neighboring planets. Rogue planets, on the other hand, may form through different mechanisms, including ejection from their original systems or direct formation from gas clouds. This distinction in formation processes suggests that rogue planets may have distinct evolutionary pathways compared to their traditional counterparts. Conclusion. Rogue planets represent an intriguing aspect of our universe, challenging conventional notions of planetary systems and formation. With their diverse characteristics, classification schemes, and differences from traditional planets, they provide a rich area for research and exploration. As we continue to refine our observational techniques and expand our understanding of these solitary wanderers, rogue planets will undoubtedly shed light on the complexities of planetary dynamics and the potential for life beyond our solar system. The study of rogue planets not only enhances our knowledge of the cosmos, but also invites us to rethink our definitions of what a planet can be. Section 2. Formation and ejection mechanisms of rogue planets. Rogue planets, those solitary wanderers of the cosmos, have sparked considerable interest in the astronomical community due to their enigmatic nature and the challenges they pose to traditional planetary formation theories. Understanding how these planets come into existence and what processes lead to their ejection from host star systems is crucial for unraveling the complexities of planetary dynamics and evolution. In this section, we will explore the various theories surrounding the formation of rogue planets and the mechanisms that can lead to their ejection. Theories on how rogue planets are formed. The formation of rogue planets remains a subject of ongoing research and debate. Several theories have emerged, each proposing different pathways through which these celestial bodies might originate. 1. Formation in protoplanetary disks. One of the most widely accepted theories suggests that rogue planets form within protoplanetary disks. the rotating disks of gas and dust surrounding young stars. In this scenario, a planet forms through the same processes that create traditional planets. As material within the disk coalesces under gravity, it can form solid bodies that grow over time. However, for some of these planets, the gravitational interactions with nearby bodies may lead to instability within the disk. This instability can result in a rogue planet being ejected from its original location, perhaps due to interactions with larger planets. Such ejections can occur in systems with multiple planets, where gravitational perturbations can disrupt the orbits of smaller bodies, casting them into interstellar space. 2. Gravitational interactions. The gravitational dynamics of a multi-planet system play a significant role in the potential ejection of rogue planets. When two or more planets influence each other's orbits, the gravitational interactions can lead to close encounters. These encounters may result in one planet gaining enough velocity to escape the gravitational pull of its host star. In particular, the process known as planet-planet scattering is a key mechanism in this context. During close encounters, one planet can transfer kinetic energy to another, potentially giving it the velocity required to break free from the star's gravitational grasp. This interaction can be more pronounced in systems with higher planet counts, where the complex gravitational dance creates a chaotic environment. 3. Instabilities in star clusters. Another avenue for rogue planet formation is through interactions in dense star clusters. In such environments, the gravitational influence of many stars can lead to chaotic interactions. When a star passes close to another star, the gravitational pull can disrupt the orbits of surrounding planets, resulting in ejections. This scenario is particularly plausible in the early stages of star cluster formation, where young stars are still in close proximity. The combined gravitational forces can create conditions that favor the ejection of planets, leading to the formation of rogue planets. As these clusters evolve and disperse, ejected planets can drift into interstellar space. 4. Direct formation from molecular clouds. Some theories propose that rogue planets may form directly from molecular clouds, the dense regions of gas and dust within galaxies. In this model, rather than forming in a protoplanetary disk around a star, a planet can emerge from the collapse of a low-mass region within a molecular cloud. This process may create free-floating planets that are not gravitationally bound to any star. These planets could be smaller than traditional gas giants, but their formation directly from molecular clouds suggests that they can arise independently of stellar systems. This theory highlights the potential diversity of planetary formation mechanisms in the universe. Processes leading to ejection from host star systems. Once formed, rogue planets can be ejected from their host star systems through various processes. Understanding these mechanisms is essential for comprehending the dynamics of planetary systems. 1. Dynamical instability. Dynamical instability is a significant factor in the ejection of rogue planets. In systems with multiple planets, gravitational interactions can lead to chaotic behavior, where small perturbations amplify over time. As planets interact, their orbits can become highly eccentric, making them more susceptible to ejection. For example, if two planets approach each other closely, one may gain enough velocity to escape the gravitational influence of the host star. This process is particularly pronounced in systems with close-packed architectures, where planets are in near proximity to one another. The resulting interactions can lead to one or more planets being flung out into interstellar space. 2. Three-body interactions. Three-body interactions are another key mechanism contributing to the ejection of rogue planets. In a system with a star and two planets, the gravitational forces can create complex dynamics. If one planet interacts closely with the star and the other planet simultaneously, the result can be a significant transfer of energy. During this interaction, one of the planets may gain enough velocity to escape the gravitational influence of the star, effectively becoming a rogue planet. This process underscores the importance of multi-body dynamics in understanding how planetary systems evolve and how planets can become unbound. 3. Stellar encounters. As mentioned earlier, rogue planets can also form due to stellar encounters in dense environments. When stars pass close to one another, their gravitational influence can disrupt the orbits of surrounding planets, leading to ejection. In crowded star clusters, these interactions can occur frequently, creating conditions conducive to the formation of rogue planets. The frequency of such encounters increases the likelihood of planetary ejection, particularly in the early stages of stellar evolution. As stars move through their clusters, the gravitational interactions can create a dynamic environment where planets are prone to being displaced from their original systems. Planetary migration. Planetary migration refers to the movement of planets within a star system due to gravitational interactions with surrounding material. In some cases, this migration can lead to instability, resulting in ejection. For instance, as a planet migrates inward or outward, it can encounter other planets, leading to close interactions that culminate in ejection. This process is particularly relevant in systems with gas giants, where the gravitational influence of these large bodies can significantly alter the orbits of smaller planets. If a gas giant migrates inward, it may destabilize the orbits of neighboring smaller planets, potentially leading to their ejection. Conclusion: the formation and ejection mechanisms of rogue planets are complex and multifaceted, offering a rich area for exploration in the field of astronomy. From the dynamics of protoplanetary disks to the gravitational interactions in dense star clusters, the pathways to becoming a rogue planet are varied and intricate. Understanding these processes not only enhances our knowledge of rogue planets themselves, but also provides insights into the broader dynamics of planetary systems and the evolution of our galaxy. As research continues and observational techniques improve, we can anticipate exciting discoveries that will deepen our understanding of these enigmatic wanderers in the cosmos. Section 3. Distribution and detection of rogue planets. Rogue planets, those solitary wanderers drifting through the cosmos, have become a focal point of astronomical research in recent years. Their elusive nature poses significant challenges for detection and study, leading to innovative methodologies aimed at understanding their distribution within our galaxy. In this section, we will delve into the various methods employed to detect rogue planets and discuss current estimates regarding their numbers in the Milky Way. Methods of detecting rogue planets. Detecting rogue planets is inherently challenging due to their lack of a star to illuminate them, making them essentially invisible in traditional optical observations. However, astronomers have developed several techniques to uncover these elusive objects, leveraging their unique characteristics and interactions with other celestial bodies. Gravitational microlensing. One of the most effective methods for detecting rogue planets is gravitational microlensing. This phenomenon occurs when a massive object, such as a rogue planet, passes in front of a more distant star, causing the light from that star to bend due to the gravitational field of the foreground object. This bending results in a temporary increase in brightness, which can be detected from Earth. Gravitational microlensing is particularly advantageous for rogue planets because it does not require them to emit their own light. Instead, astronomers can monitor distant stars for variations in brightness and identify potential microlensing events. Large-scale surveys, such as the Optical Gravitational Lensing Experiment, OGLE, and the microlensing observations in astrophysics, MOA, have successfully detected several rogue planets using this technique. 2. Direct imaging. Although direct imaging of rogue planets is difficult, advancements in technology have made this method increasingly viable. This approach involves capturing images of celestial objects in infrared or other wavelengths, often using adaptive optics to correct for atmospheric distortion. By observing regions where rogue planets are likely to be found, astronomers can identify these bodies based on their thermal emissions. Direct imaging is more effective for larger rogue planets, particularly those with significant heat signatures. Instruments like the Very Large Telescope, VLT, and the upcoming James Webb Space Telescope, JWST, are equipped with advanced capabilities to enhance the chances of detecting rogue planets through direct imaging, allowing astronomers to study their atmospheres and compositions in greater detail. Astrometric measurements. Astrometry, the measurement of the positions and movements of celestial objects, can also be used to detect rogue planets indirectly. By observing the gravitational effects that a rogue planet exerts on nearby stars, astronomers can infer its presence. This method relies on precise measurements of stellar positions over time to detect the slight shifts caused by the gravitational pull of a rogue planet. Though challenging, astrometric techniques can provide valuable information about the mass, distance, and trajectory of rogue planets. Space missions like the European Space Agency's Gaia are designed to conduct astrometric surveys, offering insights into the positions of stars and any perturbations caused by rogue planets. 4. Radio observations. Radio astronomy provides another avenue for detecting rogue planets, particularly those that may possess magnetic fields or atmospheres capable of producing radio emissions. By observing radio waves emitted from celestial objects, astronomers can identify rogue planets that exhibit unique signatures. This method is still in its infancy concerning rogue planet detection, but ongoing and future radio observatories, like the Square Kilometer Array, SKA, are expected to significantly enhance our ability to identify rogue planets through their radio emissions. 5. Spectroscopic analysis. Spectroscopy can also aid in the detection of rogue planets, particularly by analyzing the light reflected or emitted from them. By studying the spectrum of light, astronomers can gain insights into the chemical composition and atmospheric conditions of a rogue planet. This method has been successful in characterizing exoplanets within stable orbits, and as detection methods improve, it may become increasingly applicable to rogue planets as well, particularly those that can be observed via infrared or radio wavelengths. Current estimates of rogue planets in the Milky Way. Estimates regarding the number of rogue planets in the Milky Way have evolved as detection techniques have improved. Current research suggests that rogue planets may be more abundant than previously thought, leading to intriguing implications for our understanding of the galaxy. 1. Abundance estimates. Recent studies indicate that there could be billions of rogue planets in the Milky Way. A widely cited estimate suggests that there may be as many as 100,000 rogue planets for every star in our galaxy. With approximately 100 billion stars in the Milky Way, this implies that rogue planets could number in the hundreds of billions, if not more. This abundance poses significant questions about the formation and evolution of planetary systems. The sheer number of rogue planets suggests that ejection processes are common and that many planets may not remain bound to their original star systems. 2. Distribution patterns. Research also suggests that rogue planets may not be uniformly distributed throughout the Milky Way. Instead, they could be concentrated in certain regions, potentially influenced by factors such as stellar density and the gravitational dynamics of star clusters. For example, rogue planets may be more prevalent in regions of the galaxy where multiple stars and planetary systems coexist. increasing the likelihood of gravitational interactions that lead to ejection. Conversely, in sparse regions of the galaxy, rogue planets may be less common. 3. Implications for galactic dynamics. The existence of a large population of rogue planets could have profound implications for our understanding of galactic dynamics. Their movements and interactions may influence the gravitational landscape of the Milky Way, impacting the orbits of other celestial bodies and contributing to the complex dance of stellar evolution. Moreover, the presence of rogue planets may provide insights into the history of the galaxy, offering clues about the processes that shape planetary systems and the effects of stellar interactions over billions of years. Conclusion: the distribution and detection of rogue planets present both challenges and opportunities for astronomers. Through innovative methods such as gravitational microlensing, direct imaging, astrometry, radio observations, and spectroscopic analysis, researchers are beginning to uncover the mysteries surrounding these enigmatic bodies. Current estimates suggest that rogue planets could be abundant in the Milky Way, leading to exciting implications for our understanding of planetary formation, galactic dynamics, and the potential for life beyond traditional star systems. As detection techniques continue to advance, we can anticipate further revelations about the role of rogue planets in the cosmic landscape, ultimately enriching our understanding of the universe. Section 4. Environmental impact on space. Rogue planets drifting through the vastness of the galaxy without the gravitational anchor of a host star present a unique set of challenges and opportunities for our understanding of cosmic dynamics. Their presence can significantly influence the environments around them, affecting both nearby celestial bodies and the broader galactic structure. In this section, we will explore the effects of rogue planets on surrounding celestial bodies and their potential interactions with stars and other planets. Effects of rogue planets on surrounding celestial bodies. Rogue planets can have profound impacts on the celestial bodies they encounter, primarily due to their gravitational influence. As they traverse the galaxy, their interactions can lead to a variety of outcomes for nearby objects, including asteroids, comets, and other planetary bodies. 1. Gravitational perturbations. One of the most immediate effects of a rogue planet's passage is its gravitational perturbation on nearby celestial bodies. As a rogue planet moves through space, it can exert gravitational forces on other objects, altering their orbits and trajectories. These perturbations can result in several scenarios. Orbital changes. Nearby asteroids and comets may experience shifts in their orbits, potentially leading to destabilization. In some cases, these changes can increase the likelihood of collisions or ejections from their original paths. Capture of small bodies. A rogue planet can capture smaller celestial bodies, drawing them into its gravitational field. This can lead to the formation of temporary or permanent satellite systems around the rogue planet, creating a unique environment for the captured objects. Impact on asteroid belts. Rogue planets can significantly influence asteroid belts in their vicinity. As they pass through these regions, their gravitational interactions can disrupt the orbits of asteroids, potentially leading to collisions among them or with other celestial bodies. Such disruptions can result in fragmentation of asteroids. When a rogue planet's gravitational pull alters the orbits of asteroids, collisions may become more likely, causing fragments to scatter throughout the asteroid belt. This fragmentation can lead to new, smaller bodies that may eventually become rogue planets themselves. Increased meteor activity. If a rogue planet disrupts a dense asteroid belt, the resulting fragments may be ejected into space, increasing the likelihood of meteor showers on nearby planets or celestial bodies. 3. Interactions with comets. Rogue planets can also interact with comets, which are generally more sensitive to gravitational influences due to their typically elliptical orbits. As a rogue planet approaches a comet, several outcomes can occur. Deflection of comets. The gravitational pull of a rogue planet can alter the trajectory of a comet, potentially sending it into a new orbit, or even ejecting it from the solar system altogether. This deflection can lead to unpredictable behavior and changes in the comet's path. Increased activity. Comets that come close to a rogue planet may experience increased activity, such as outgassing and tail development, due to the gravitational forces acting on them. This can lead to more pronounced features and changes in their appearance. Potential interactions with stars. Rogue planets, while not gravitationally bound to any star, can still interact with stars they encounter during their journeys through the galaxy. These interactions can have significant consequences for both the rogue planet and the star involved. 1. Close encounters with stars. When a rogue planet approaches a star, the gravitational interaction can lead to dramatic outcomes. The strength of these interactions depends on the mass of the rogue planet and the star, as well as their relative velocities. Possible scenarios include gravitational capture. In rare cases, a rogue planet may be captured by a star's gravitational field, becoming a new member of the star system. This process can occur if the rogue planet passes close enough to the star, losing energy in the process and settling into a stable orbit. Ejection from the galaxy. If a rogue planet passes too close to a massive star, it may gain enough velocity to be ejected from its original trajectory, potentially spiraling into interstellar space. This scenario highlights the dynamic and unpredictable nature of celestial interactions. 2. Influence on stellar dynamics. The presence of rogue planets can also impact the dynamics of star clusters and other celestial systems. In densely populated regions, the gravitational interactions between rogue planets and stars can lead to stellar migration. Rogue planets can influence the movement of stars within a cluster, altering their orbits and potentially leading to the formation of new stellar systems. This interaction contributes to the complex dynamics of star clusters, where multiple bodies interact gravitationally. Formation of new planets. As rogue planets interact with stars, they may also trigger the formation of new planetary bodies. The material ejected during close encounters or collisions can coalesce to form new planets, enriching the diversity of celestial systems. Interactions with other planets. Rogue planets can also have significant interactions with other planets they encounter in their travels. These interactions can lead to various outcomes, ranging from gravitational influences to potential collisions. 1. Planetary scattering. Similar to the gravitational perturbations experienced by asteroids, rogue planets can cause scattering among other planets. When a rogue planet comes close to a planetary system, it may influence the orbits of existing planets, leading to orbital instability. Orbital instability. The introduction of a rogue planet into a planetary system can destabilize the orbits of existing planets. This instability may result in orbital shifts, leading to collisions or ejections of planets from the system. Formation of new resonances. As a rogue planet interacts with other planets, it can create new gravitational resonances, resulting in altered orbital patterns. These resonances can lead to long-term stability or instability within the planetary system, affecting its evolution over time. 2. Potential collisions. In some instances, the trajectory of a rogue planet may intersect with that of another planet, leading to a potential collision. While such events are rare due to the vastness of space, they can have catastrophic consequences for both bodies involved. Possible outcomes include destruction of smaller bodies. If a rogue planet collides with a smaller planet or moon, the resulting impact could lead to fragmentation and the creation of debris fields. This debris may contribute to meteor showers or form new celestial objects. Altered planetary environments. A collision with a rogue planet could drastically alter the environment of the impacted planet. Changes in atmosphere, surface conditions, and geological activity may result from such an event, potentially affecting any existing life forms or future habitability. Conclusion: the environmental impact of rogue planets on surrounding celestial bodies and their interactions with stars and other planets presents a fascinating area of study in astrophysics. Through gravitational perturbations, close encounters, and potential collisions, rogue planets can significantly influence the dynamics of their environments. As we continue to explore and detect rogue planets, gaining a deeper understanding of their interactions will enhance our knowledge of planetary systems, galactic dynamics, and the complex relationships that shape the universe. The study of rogue planets not only illuminates the nature of these enigmatic wanderers, but also challenges our understanding of the intricate tapestry of cosmic relationships that govern the cosmos. Section 5. Implications for life on rogue planets. Rogue planets, those solitary wanderers that drift through the vastness of space without a star to anchor them, present a compelling area of study when it comes to the search for extraterrestrial life. Traditionally, the search for life beyond Earth has focused on planets located within the habitable zones of stars, where conditions may be suitable for liquid water to exist. However, the existence of rogue planets challenges this notion and raises intriguing questions about the potential for life in environments that are vastly different from those we have typically considered. In this section, we will explore the potential for life on rogue planets and how they compare to traditional habitable zones around stars. The potential for life on rogue planets. While rogue planets lack the steady warmth provided by a nearby star, they may still possess conditions that could support life. Several factors contribute to the potential habitability of these celestial bodies. 1. Internal heat sources. One of the most significant factors that could enable life on rogue planets is the presence of internal heat sources. Even without solar energy, rogue planets can retain heat generated during their formation or from radioactive decay within their cores. This residual heat may create subsurface environments where liquid water could exist. Subsurface oceans. Some rogue planets may harbor subsurface oceans beneath icy crusts, similar to what is hypothesized for some moons in our solar system, such as Europa and Enceladus. These oceans could provide the necessary conditions for life, shielded from harsh surface environments. 2. Atmospheric retention. Rogue planets may be capable of retaining atmospheres, which can play a crucial role in supporting life. The presence of a thick atmosphere could help insulate the planet, trapping heat and creating more stable conditions. Factors influencing atmospheric retention include planetary mass. Larger rogue planets may have stronger gravitational fields that can hold on to atmospheres more effectively, increasing their potential for habitability. Geological activity. If a rogue planet exhibits geological activity, it could release gases that contribute to the formation of an atmosphere. Volcanic activity might also create conditions suitable for chemical processes that could support life. 3. Chemical diversity. For life to exist, a planet must have the necessary chemical building blocks. Rogue planets may provide diverse environments with rich chemical compositions, potentially resulting from their formation processes or interactions with other bodies. The presence of essential elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur is critical for the emergence of life. Complex chemistry. The lack of sunlight on rogue planets may encourage alternative biochemical pathways, leading to unique forms of life that do not rely on photosynthesis. This could result in ecosystems that thrive in dark, cold environments, similar to extremophiles found in extreme conditions on Earth. Potential for microbial life. Even if conditions are not ideal for complex life forms, Rogue planets may still harbor microbial life. Extremophiles on Earth have demonstrated that life can survive in extreme environments, such as deep-sea hydrothermal vents and subglacial lakes. These organisms could serve as a model for the types of life that might exist on rogue planets. Survival mechanisms. Microbial life may develop unique adaptations to endure the harsh conditions of a rogue planet, such as low temperatures, high pressures, and limited energy sources. The potential for life in these environments expands our understanding of what constitutes a habitable world. Comparison with habitable zones around stars. The concept of habitable zones, HZs, has traditionally guided the search for extraterrestrial life. These zones refer to regions around stars where conditions may be just right for liquid water to exist on a planet's surface. However, the existence of rogue planets challenges the notion that habitability is solely dependent on proximity to a star. 1. Defining habitable zones. Habitable zones are typically classified into 3 categories based on distance from a star. Inner habitable zone, the region closest to the star, where planets might experience temperatures conducive to liquid water, but risk becoming too hot for habitability. Optimal habitable zone, the region where conditions are just right for liquid water to exist, often referred to as the Goldilocks zone. Outer habitable zone, the region furthest from the star, where planets may be colder but still capable of maintaining liquid water under certain conditions. 2. Rogue planets and alternative habitats. Rogue planets exist outside the parameters of traditional habitable zones, yet they may still host conditions favorable for life. The potential for internal heat sources, persistent atmospheres, and complex chemical environments allows rogue planets to create unique habitats that differ from those found in star systems. Broader definition of habitability. The existence of rogue planets suggests that our understanding of habitability must be broadened. Rather than limiting our search to planets within habitable zones, we should also consider the diverse environments that rogue planets may offer. 3. Energy sources for life. While stars provide a consistent energy source for planets within habitable zones, rogue planets must rely on alternative energy sources. The potential for geothermal activity and chemical processes can create environments conducive to life, albeit in different ways than those reliant on solar energy. Geothermal and chemical energy. Life on rogue planets may derive energy from geothermal sources, such as hydrothermal vents, or from chemical reactions occurring within their subsurface oceans. This highlights the adaptability of life and its potential to thrive in varied environments. 4. Implications for exoplanet research. The potential for life on rogue planets has significant implications for exoplanet research. As astronomers continue to explore the cosmos, expanding the search criteria to include rogue planets could lead to the discovery of new and unexpected forms of life. Future missions. Upcoming missions and observatories, such as the James Webb Space Telescope, JWST, may enhance our ability to detect rogue planets and analyze their atmospheres. This could provide insights into their potential habitability and the possibility of life. Conclusion. The implications for life on rogue planets challenge our traditional understanding of habitability and the conditions necessary for life to thrive. While these planets lack the stable environments provided by stars, they may still host unique conditions that could support life, particularly in subsurface oceans or under thick atmospheres. The existence of rogue planets broadens our perspective on the potential diversity of life in the universe and encourages us to reconsider the parameters of habitability. As we continue to explore the cosmos and refine our detection techniques, rogue planets may reveal new frontiers in the search for extraterrestrial life, expanding our understanding of the complex tapestry of life beyond Earth. Section 6. Philosophical and scientific considerations. Rogue planets, drifting through the cosmos without the gravitational bonds of a host star, challenge our understanding of planetary systems and the nature of existence in the universe. Their solitary paths raise profound philosophical and scientific questions that extend beyond the realms of astronomy and astrobiology. In this section, we will explore the implications of rogue planets in the context of the universe's structure and their significance for the search for extraterrestrial life. Rogue planets in the context of the universe's structure. The existence of rogue planets invites us to reconsider the organization and dynamics of our universe. Traditionally, we've conceptualized planets as components of star systems, bound by gravitational forces and functioning within the framework of a galaxy. However, the presence of rogue planets introduces complexities that challenge this conventional view. 1. Cosmic isolation versus connectivity. Rogue planets symbolize a form of cosmic isolation, wandering through interstellar space without the gravitational influence of a star. This raises questions about the nature of existence and the interconnectedness of celestial bodies. Are rogue planets truly isolated, or do they play a role in the broader cosmic web? Their movements may interact with other celestial objects, influencing the dynamics of galaxies and star clusters. Galactic interactions. Rogue planets can affect the distribution of matter in the galaxy, potentially influencing star formation and the behavior of other celestial bodies. This interconnectedness suggests that even seemingly isolated objects can have far-reaching implications for the structure and evolution of the universe. Revisiting planetary definitions. The existence of rogue planets compels us to reconsider what constitutes a planet. Traditionally, planets are defined by their orbit around a star, but rogue planets challenge this definition. Should we classify them as planets despite their lack of a stellar companion? This question opens up discussions about the criteria we use to define celestial bodies and the implications of those definitions for our understanding of the universe. Expanding definitions. By broadening our definitions to include rogue planets, we acknowledge the diversity of planetary environments and the various pathways to planetary formation. This expansion can enrich our understanding of planetary science and the complexities of celestial dynamics. The nature of life in the cosmos. The existence of rogue planets prompts us to explore the nature of life in the universe. If life can emerge in environments that are vastly different from those we consider habitable, what does this mean for our search for extraterrestrial life? The potential for life on rogue planets challenges the anthropocentric view of habitability and encourages us to consider alternative forms and pathways for life. Diversity of life forms. The variety of environments in which life could exist raises questions about the diversity of life forms. Could rogue planets harbor life that is entirely different from what we know, adapted to extreme conditions? This possibility expands our understanding of biological systems and the resilience of life. Implications for the search for extraterrestrial life. As we expand our exploration of rogue planets, their implications for the search for extraterrestrial life become increasingly significant. The traditional focus on habitable zones around stars may need to be reevaluated in light of the potential for life in environments devoid of stellar energy. 1. Redefining habitable zones. The concept of habitable zones has been central to the search for extraterrestrial life. These regions around stars are characterized by conditions suitable for liquid water, a key ingredient for life as we know it. However, rogue planets challenge this notion, suggesting that life could exist beyond these traditional boundaries. Internal heating as a factor. Rogue planets may generate internal heat through geological activity or radioactive decay, creating subsurface environments that could support liquid water. This redefinition of habitable zones expands the search for life beyond well-defined areas around stars. Broader search parameters. The inclusion of rogue planets in the search for extraterrestrial life necessitates broader search parameters. Current detection methods primarily focus on exoplanets within habitable zones, but the potential for life on rogue planets suggests that our criteria for identifying candidate worlds should be more inclusive. Innovative detection techniques. Developing new techniques for detecting rogue planets will be essential. Methods such as gravitational microlensing, radio observations, and studies of chemical signatures in atmospheres could reveal the presence of these planets and their potential habitability. Astrobiological considerations. The study of rogue planets also has implications for astrobiology, the field dedicated to understanding the potential for life beyond Earth. As we explore the environments of rogue planets, we must consider the biochemical processes that could underpin life in these unique settings. Alternative biochemistries. Life on rogue planets may not rely on the same biochemical pathways as life on Earth. The study of extremophiles, organisms that thrive in extreme conditions on our planet, can provide insights into the types of life that may exist in the harsh environments of rogue planets. Philosophical reflections on life. The potential for life on rogue planets raises profound philosophical questions about the nature of existence and the uniqueness of life in the universe. If life can emerge in such diverse environments, what does this mean for our understanding of consciousness, intelligence, and the role of life in the cosmos? Philosophical reflections on life. Uniqueness versus commonality. The possibility of diverse life forms challenges the notion of humanity's uniqueness in the universe. It invites us to reflect on our place within the broader tapestry of existence and the potential for shared experiences across different forms of life. Conclusion. Rogue planets present a fascinating intersection of philosophical and scientific considerations, prompting us to rethink our understanding of the universe's structure and the nature of life itself. Their existence challenges traditional definitions of planets and habitable zones, expanding our perspective on the potential for extraterrestrial life. As we continue to explore these enigmatic wanderers, we may uncover not only new worlds, but also new insights into the resilience of life and the interconnectedness of the cosmos. The study of rogue planets thus holds the promise of enriching our understanding of existence and the diverse possibilities that inhabit the universe. Conclusion. Understanding rogue planets. Rogue planets, those enigmatic wanderers that drift through the cosmos without the gravitational bonds of a host star, have emerged as a compelling area of study in contemporary astronomy. Their unique characteristics challenge traditional definitions of planets and habitable zones, prompting researchers to reassess the conditions under which life might arise. In this conclusion, we will summarize the key points discussed throughout this report and outline future directions for research on rogue planets. Summary of key points. 1. Definition and characteristics of rogue planets. Rogue planets are defined as planetary bodies that do not orbit a star, instead moving freely through interstellar space. They can vary significantly in size, composition, and temperature, ranging from gas giants to smaller, rocky bodies. Their isolation raises questions about planetary formation and the mechanisms that lead to their ejection from host star systems. 2. Formation and ejection mechanisms. The formation of rogue planets can occur through several pathways, including formation within protoplanetary disks and ejection due to gravitational interactions with other planets or stars. Gravitational perturbations and dynamical instabilities play significant roles in the ejection process, leading to a diverse population of rogue planets across the galaxy. 3. Detection methods. Detecting rogue planets poses unique challenges due to their lack of a direct light source. However, astronomers have developed several innovative methods, including gravitational microlensing, direct imaging, astrometric measurements, and radio observations. These techniques allow researchers to identify and study rogue planets, contributing to our understanding of their properties and distributions. 4. Environmental impact. Rogue planets can significantly influence their surroundings, exerting gravitational effects on nearby celestial bodies. Their interactions can destabilize asteroid belts, affect the orbits of comets, and even lead to collisions with other planets. These dynamics highlight the interconnectedness of celestial systems and the broader implications of rogue planets within the galactic structure. 5. Implications for life. The potential for life on rogue planets challenges traditional notions of habitability, as these planets may harbor subsurface oceans and retain atmospheres despite their distance from stars. The existence of life in extreme environments, such as those on rogue planets, invites us to reconsider the diversity of life forms that might exist beyond Earth. 6. Philosophical considerations. Rogue planets force us to confront deeper philosophical questions about the nature of existence, the definitions of planets, and the potential for life in the universe. Their presence enriches our understanding of the cosmos and invites reflections on humanity's place within it. Future directions for research on rogue planets. As our understanding of rogue planets continues to evolve, several future research directions hold promise for expanding our knowledge in this field. 1. Enhanced detection techniques. Advancements in observational technology will be crucial for identifying rogue planets more effectively. The upcoming James Webb Space Telescope, JWST, and other next-generation observatories are expected to significantly enhance our ability to detect and analyze rogue planets. Developing new techniques, such as improved gravitational microlensing methods and enhanced spectroscopic analysis, will also be essential for uncovering the properties of these elusive bodies. 2. Characterization of rogue planet atmospheres. Investigating the atmospheres of rogue planets could provide critical insights into their potential habitability. Future research should focus on characterizing the chemical compositions and thermal properties of rogue planets, particularly those that may retain atmospheres. Understanding the processes that govern atmospheric retention and evolution in the absence of stellar energy will be key to assessing their potential for supporting life. 3. Exploration of subsurface environments. Research should also prioritize the exploration of subsurface environments on rogue planets, where conditions may be conducive to life. Understanding the geology, thermal dynamics, and potential for liquid water beneath icy crusts will be essential for evaluating the habitability of these worlds. Investigating analogs on Earth, such as subglacial lakes and deep-sea hydrothermal vents, can offer valuable insights into the types of ecosystems that may exist on rogue planets. 4. Theoretical models and simulations. Developing theoretical models and simulations of rogue planet dynamics will be crucial for understanding their formation, ejection mechanisms, and interactions with other celestial bodies. These models can help researchers predict the distribution and abundance of rogue planets in the galaxy, guiding observational efforts and enhancing our understanding of their role in cosmic evolution. 5. Interdisciplinary collaboration. Finally, fostering interdisciplinary collaboration among astronomers, astrobiologists, geologists, and philosophers can enrich the study of rogue planets. By integrating insights from various fields, researchers can develop a more holistic understanding of the implications of rogue planets for planetary science, astrobiology, and our philosophical perspectives on life and existence. Thank you for watching. We hope you enjoyed today's video. If you did, don't forget to hit that like button and subscribe to our channel for more exciting content. Your support means the world to us. We can't wait to see you back here for our next adventure. If you have any feedback or ideas for future videos, drop them in the comments below. Until next time, take care and stay awesome. See you soon.